So this video I am making just for my AP Physics 2 students, just to get by for our asynchronous learning on Friday. And it's not one of my better videos, so take it for whatever it's worth. In the last class we learned how the magnetic force is created because when a charge moves, there's a magnetic field around it. And there is a right-hand rule that our thumb points to the right and our four fingers curl around in the direction of the magnetic field of a moving charge. When that magnetic field hits another magnetic field, there will be a force given by a second right-hand rule. Okay? And we found that the variables that are going to affect the magnitude of the force would be how much charge was going through there. More charge would be a stronger magnetic field interacting with this magnetic field, so more force. If that charge moved faster, it would be creating a bigger disturbance in space-time and would have a larger magnetic field. Or if this magnetic field hit a stronger magnetic field here, that would also do it. So Q, V, B are the variables that are going to affect the magnetic force, and then we just multiply by the sine of the angle to find a component of its velocity that is perpendicular to the magnetic field. If it's parallel, there's no force. Okay, that was a quick review. Now, what happens if I don't just shoot single charges through that magnetic field, but I shoot a whole line of charges through a wire? That's just current running through that wire. Well, when current is running through that wire, there's a magnetic field around each individual charge, and the magnetic field of that is going to interact and create a force in the up direction as well. Okay? All right. Now let's do some algebraic magic here. Let's say that that wire was a certain length. Okay? So there's going to be a certain number of charges in that length. And what I'm going to do here is we said that the force was QVB, but the velocity is just the distance those charges went divided by time. So the distance would be the length of that wire divided by the time it takes a charge to go that distance. Okay, so just length divided by time is velocity. And that was magic. No, that wasn't magic. Let's show you the real magic. Ready for the real magic? There it is. You see the magic? If I, instead of divide length divided by time, I divide charge by time. But what's charge divided by time? Well, it's the number of charges that go by every second. That's current. Okay, and we are ready to check off another equation off our equation sheet. So this one is dealing more if single charges move at some velocity through a magnetic field, there's a force. But if I have a whole bunch of charges all channeled in a wire, and we know the current in amps running through that wire, and the length of that wire that is in this magnetic field, we can also calculate the force. Okay, so we're going to check that off of our equation sheet. And we did briefly cover the vector cross product. I just want to throw that out there and just remind you that you will not see or be asked of a question on the AP exam that asks you to take the cross product. But just a refresher, when we see the bars over here, we're just taking the magnitude of that vector quantity. So just the size of it. But when we do it this way, we would actually still be left with magnitude and direction. If we do it in IJK notation, then we would get a value for the magnetic force, a value multiplied by an I, a unit vector in the I direction, and then a unit vector in the J direction, and a unit vector in the K direction, X, Y, Z. Okay, so check, check, check. Same thing here, but this is now just a wire of a certain length and has current in it. And then the same thing, we just want to find a component of that current that is perpendicular to the magnetic field, not parallel to. All right, when we first introduced magnetic fields, we gave you a right-hand rule that says you point your thumb in the direction of the conventional current, and there's a magnetic field around that wire. So if this is connected to the positive side of the battery, and this is to the negative side, conventional current goes from positive to negative. So I would be pointing my thumb down, grabbing the wire, and my forefingers are going to wrap around like this. And I haven't quite shown it like this before. I've just shown like a single loop going around. But what I'm trying to show with this picture is that the magnetic field close to that wire is going to be pretty strong. And the further and further we get away from that wire, the weaker and weaker the magnetic field is going to get. Not too surprising. And remember, we talked about the gravitational field, that the gravitational field was inversely proportional to the square of the distance. Or we also said that the gravitational field was inversely proportional to the spreading out of its area. On this surface here, if we go twice as far, the area became 4 times as much. And if we go 3 times as far, the area became 9 times as much. So the gravitational field was inversely proportional to the square of the area. That's not what's happening here. What do you think? The field gets weaker and weaker and weaker and weaker and weaker, but it's not inversely proportional to the square of the area. It's inversely proportional to the circumference of this circle. So this has a very small circumference. If I went twice the distance, the circumference would become twice as big. So that magnetic field has gotten half as strong. So here's what we're saying. B is our magnetic field, and the magnetic field around a wire is proportional to how much current is running in that wire, and then and inversely proportional to the circumference. So if we go double the distance, we would get half the field. If we go 4 times the radius, we would get 1/4 the field. Okay, and let me back up. If this is proportional to those things, we can set them equal if we drop in the right proportionality constant. And with electric fields, we had this constant called epsilon sub naught. It was the permittivity of free space. It was how well empty space permits electric fields to get set up. This is a different one. This is called mu sub naught, and this is the permeability of free space. Not the permittivity, but the permeability. How well magnetic fields permeate through free space. And there's supposed to be a difference there, and I don't understand the difference. Okay. Anyway, right here, very strong field close to the wire. Further away, the magnetic field gets weaker and weaker and weaker, but it gets weaker as an inverse relationship. Not an inverse square, just a straight up inverse relationship. So that if the radius and the strength of the field are inversely proportional. 9 times the distance, 1/9 the strength of the field. So we can check this equation off our equation list as well. This is just tells us how strong the magnetic field is around a wire that is carrying current. Depends on how much current is running through and how far we are from that wire. Okay. Oh, and by the way, the permeability of free space, or the vacuum permeability, is 4 pi times 10 to the negative 7 Tesla meters per amp. okay? Because we just have to take amps and meters and get a unit in Teslas. All right, let's see how we're going to do this now with 2 wires. We have current running from positive to negative in this wire, and we have current running from positive to negative in this wire. And I am saying that they have the same current. There's going to be a magnetic field around this wire, and there's going to be a magnetic field around this wire. Where will the magnetic field be equal to 0? At point A, point B, or point C, or D? There is no place where the magnetic field around those wires will be 0. I'm asking you to hit pause, so hit pause and think about it now. You better have hit paused. Don't deprive yourself of an opportunity to make synaptic connections in your brain. But what we can do is we can use our right-hand rule here and say that there is a magnetic field going around that wire like this. And there's a magnetic field going around that wire like this. So above this wire, the magnetic field is coming out of the screen. Under this wire, the magnetic field from that one is going in to the screen. And so our answer is B here, because they have the same current, and if I go the same distance from each of those, the same current and the same distance will have the same strength of the field, but one is going into the screen and the other is coming out of the screen. So they are going to cancel each other out and have no net magnetic field right there. All right, I'm going to hit pause here in just a moment, but where will the magnetic field be 0? This time the current is running in opposite directions, and this wire here has twice as much current as this wire does here. So go ahead and hit pause and think about it. Go now. All right, I'm back because you hit pause and now you're playing again. But where is the magnetic field between the two wires equal to 0? Well, we're going to use our right-hand rules here again. And this wire here has current running from positive to negative, so there's current running around it like this. And there's a magnetic field going around it like this and a magnetic field going around it like this. I drew this one thicker, bigger, because it had twice as much current. Twice as much current would be twice the field. So they're not going to cancel out right here in the middle. They're going to cancel out up here at A, okay? Because the lower wire here had twice as much current, you would have to be twice as far from it to have the same strength of field. So point A here is twice as far from the lower wire as point A is from here. The upper wire has a magnetic field coming out of the board, and the magnetic field of this one is going to be going into the screen at that same location. Same magnitude, opposite direction, the magnetic field is 0 right there. All right, now, oh boy, here's what we're going to do. If we had current running through the wire, and I am trying to show this maybe different than I ever have. Remember that X's is a magnetic field going into the board. Dots are magnetic fields coming out of the board. But when the magnetic field lines are closer together, it's a stronger magnetic field. Where the magnetic field lines are farther apart, a weaker magnetic field. So this is showing two things. It's showing the magnetic field is coming out of the screen, under the wire and into the screen above, but it is also showing that the further we get from it, the weaker it becomes. And it is given by that equation. Okay? Now what we want to do, well, I guess this equation here could calculate how strong the field would be out here at some distance. So if I know the current and the distance and the permeability and 2 and pi, I can calculate the strength of that field. All right, you ready for this? We're going to have a second wire, and that second wire is going to have current running through it. So the way we're thinking about it is that this wire here has current running through it, creating a magnetic field. And then we have current in a magnetic field. The current of this wire is in the magnetic field of that wire. So I'm going to ask you to pause here in just a second again, but I want you to use your right hand and predict, is the green wire going to be moved with magnetic force up or down, toward us, or away from us? Okay, so hit pause and use your right hand rule to predict the direction of the force on the green wire. I sure hope you did that. I really hope you did. But right hand rules, we point our thumb to the left for the green wire. Our forefingers are coming out of the screen, so you have to kind of hold the palm of your hand up over your shoulder to get your thumb pointing left and your forefingers pointing out. The palm of your hand is pointing up, and so there is a magnetic field, a magnetic force up. Okay? All right. That was just predicting the direction of the force. I wonder if we could calculate the magnitude of that force. The lines over there would calculate the magnitude. Well, if I knew how much current was running through that wire, and I knew the length of that wire, and I made sure that it was at a 90-degree angle, so the component of sine gives us that, and then I had to know the strength of the field. Oh dear, how could I find the strength of the field that green wire is experiencing? Oh, right there. That's how I'm going to calculate the strength of the field that this green wire is experiencing. Okay, so this is how we calculate the strength of the field some distance from this yellow wire. Okay, and we just substituted that in there. Okay, we are going to do a lab on Monday that is very, very, very technical. And we're going to measure the magnetic force between two wires. Okay, we're going to measure the force between these two wires. And the force is really, really, really small. Okay, much smaller than a Newton, much smaller than a tenth or a hundredth. It might even be smaller than a thousandth of a Newton. Okay, we're going to measure a really, really small force, and we have to have kind of an elaborate design to be able to measure that force. But we are going to measure the permeability of free space. And that's what we're going to do Monday. And this idea is, we have to hold very dearly onto that idea. Okay, so our I can statements. I can describe the magnitude and direction of a force on a charge moving through a magnetic field. Okay, so this is like single charges or just point charges. If we knew the magnitude of the charge, the velocity and the strength of the field, and the angle, I can calculate the magnetic force. Describe the magnitude and direction of the force of a wire with current moving through a magnetic field. Okay, so that was where we just took velocity divided by time, distance divided by time was velocity, but I divided the charge divided by time and got current. Relate the strength of the magnetic field around a wire to the distance from the wire, and there we go. And then describe the magnitude and direction of the force between two parallel wires with current running through them. All we're doing is taking this and substituting it in for right there. Okay, that is it.